So, can I start?
Yes, sir.
Yes, sir.
So this is where we are emphasizing that when you store a material, we wanted that to come out uniformly. That is the critical part. And often, if you make any improper design, you will see flow obstructions. So, what are all different flow problems can happen in the silos? Here, I'm just putting what are all the flow problems that occur in the silos. One is called arching. Arching means the solids will flow after some time. It will make an arch. It will make an arch. So once it's made an arch, the solids will not flow out. Once it formed an arch, the solids will not come out. So the arching happens because of various factors like the if there is a huge, like if there is a lot of moisture and if there is a strong interaction between the particles because of this moisturizing conditions, then this arching will happen. I request the student to mute your mic. Yeah, thank you. Do you have any question to ask me? If not, you don't unmute, so that is fine. So this is arching. sometimes in a while when you open the rotary valve, what we observe is that there is a stagnant zones will form. This is one stagnant zone, and this is some other stagnant zone. Stagnant zone. Only the flow takes place only in the middle. The flow takes place only in the middle, and it forms like a small channel or a hole that we call rat hole. In the flow of particles in such rat holes, we call it as a funnel flow. It makes like a funnel, right? It's almost like a funnel shape. Almost like a funnel shape. So whenever there is a stagnant zones, in the particles, this sort of funnel flow or rat flow, so rat hole formation and funnel flow will takes place. So in a few minutes later, I will explain why this segregation stagnant zones will happen. I will explain. Whenever there is a funnel flow, what happens is that sometimes there won't be any uniform flow. Whenever there's a funnel flow, sometimes there could be uniform flow, but whenever there's a rat hole, what will happen is that the particle gets stuck and suddenly will fall down. I showed you in the previous video the way you store matters. I showed you based on the angle, cone angle. In one video I showed the uniform flow of the particles. In another video showed stops, falls. That is called flooding. Suddenly a lot of material falls and suddenly no material will come. And that can always damage, depends on the quantity of material comes out, that can damage the conveyor, which is used for transporting the solids. So such condition is called flooding. Now, another thing is called segregation. Whenever you are storing the particles of different sizes, some of them small and some of them big. Whenever you have a distinct size difference, when you fill the silos, students, just a doubt, Are you getting any background noise from my mic? Or it's clear? The voice is clear.
Sir, it is
Voice
clear.
is clear. Your voice
It is
is
Clear,
clear.
right?
Yes.
Okay, thank you. So whenever you have a particles of different sizes, the distinct, like this is see, this is small and this is big, and the difference is sufficient enough. When you fill the container, right, what will happen is that the finer particles tend to form in the middle, and the bigger solids tends to go outside, stay away and far away from that. That way, you are seeing that there is segregation of particles will take place. Segregation of particles will take place. This segregation can cause stagnant zones and can cause other problems. That is why, if possible to have uniform size, if there is a possibility, we can maintain the uniform size. If not, we have to use other techniques to avoid the segregation. So whenever there is segregation, you can see the formation of stagnant zones, funnel flow, rat hole can take place. This is the one of the important reason to formation of the stagnant zones. If you want to avoid funnel flow, while you are filling the store silos, you have to make sure that the uniform particles takes place. Otherwise, we have to use different other methods which I show in the next slide while filling the silo. That way you can avoid the funnel flow. That is one reason. Few other reasons also there. Segregation is one reason to create the funnel flow or rat holes. Now, whenever there is a segregation, another problem is non-uniform discharge. Non-uniform discharge. Like let's say the segregation zone is formed this way, then what happens? Only the solids will come out from this zone, and all these solids will become the stagnant. And this called suddenly will fall, and whole silo can get broken, and that is called buckling effect. Sometimes industries in olden days, they used to equip with some sonic waves, and which will make vibrate the silos to create this funnel flow. But this way, somehow to avoid this, for the destroy the solids, whenever there is a stagnant zones, whenever there is a rat hole, whenever there is funnel flow, to speed up the process, they used to vibrate. They used to vibrate the whole silo. The problem is the vibration can lead to the disturbed solids, but definitely won't be uniform. Second thing is cost a lot of money and it makes a lot of noise in the industry. That is why what are all factors which is causing these flow problems? What are all the factors which is causing these flow problems? We have to understand. And if you design properly, if you maintain proper conditions, then you can avoid all these problems: arching, rat hole, flooding, segregation. All this can be avoided, mitigated. Whenever it comes to the particle technology, the people thinks that this is a very old technology. So we don't have to pay attention. We don't have to learn. That's why they won't pay attention. But these are all must, right? These are all must. Storage of solids is must. Storage of solids before entering the reactor or after products, because most of them products are solids. Most often products are solids. So we have to know very well. That's why in the before 10 years or so, very less attention. Again, it's picking up because people understanding the value of it. So a lot of research has done much earlier days. In between, very, very less emphasis gone, but again picking up because these very important factors. These are very simple factors, these are whatever I'm explaining is very, very simple. But we all have to keep an idea. We all have to have idea whenever we're dealing in industry problems, whenever we're working in industry as a process engineer. So here, there's another way also segregation happen. Let's say the big solids, if the solids are very big and they're very less, then there's also possibility that the fine solids can go out and the big solids can come in between. That is also possible for the segregation. I just put a YouTube video you all can watch later. Here there is a sand. when you there's a sand bed, when they drop a solid sphere, when they drop solid sphere, how this solid sphere goes and segregates itself, it will show. And there is another video I actually could not find yesterday night, but there is a very interesting video. One person, it's a very simple phenomenon, not at all very great phenomenon. He put a steel ball and he filled a sand. First one is that there is sand bed and someone has dropped a steel ball. Second one is that someone put a steel ball first, then he filled with the sand. Now if you just hit this one, you just hit this whole bottle or box, right? You will find out that the steel ball will come outside. The steel ball will come outside because of this segregation phenomena. Because of this segregation phenomena. Segregation easily happens in a flowing solids. So how do we avoid segregation when we store solids? When we store solids in a, like when you fill the silos, not store, when you fill the silos, right? The segregation happens while filling the silos. The segregation happens when you fill the silos. So this is the chute, the feeder, the chute or the feeder, right? The feeder, when it flows off, obviously we know that the light density particles, see the velocity of the light density particle and heavy particles are differs, right? Both are being discharged at the same velocity from the tube, but when it comes outside and the way it settles, the way it carry velocity, the way it moves are completely depends upon the surround fluid conditions, So you will see the fine particles will fall at one place and big particles will fall at other place. And this is in the normal plate. You will see same phenomena in the silos also. The same phenomena also happens in the silos also. This way, either discharge can dominate by this or the discharge can dominate by this. Whatever particles comes first to the below discharge, that will dominate. So obviously other zone will become the stagnant. Then all flow problems can take place. All types of flow problems can take place. Similarly, the particles coming out from conveyor belt can also do the segregation depends on this one. So this is our again YouTube video, a technique which explains how the segregation cannot happen. Same thing, whatever I'm showing in this slide, same thing being demonstrated in a simple video form. Okay, you all can watch later. So whatever I'm explaining in this slide is being demonstrated with a video in this YouTube video. Sorry. So if you don't want segregation to happen, the feeder, the chute, the feeder can move, rotate. Instead of putting it only one location, you can continuously rotate it. Just like this, rotate. I'm just showing, you all can see my video, just rotating like this. That way, you will not have segregation one place. Another one is, there's a cone, right? By placing a cone, the particles tends to hit and fall at the uniform rate. Inclined cone, straight cone. So the cone, of course, different ways to put in the cone, but the cone, placing the cone helps very much to avoid the segregation. Or you can fill at the multiple locations, or you can fill at through multiple inlets, filling at the multiple inlets. But the cone is more effective. The cone of all the things, the cone is more effective because the hitting on the cone and falling reduces that settling velocity criteria. And when we come to the particle dynamics in the fluids, you will understand more better how the settling phenomenon and how other factors influence. Okay. Hope you all understood how the segregation forms and how to avoid the segregation. Any student have any questions at this point of time? If no questions, fine. Okay. Hope you all understood. If you understood, that is enough for me. Because I could have easily run through slides so easily, but my aim is you all should understand what you are listening. Somehow, whatever is it should make sense. You all should understood, so that it will be easy, right? If you have to again study and read the books and what is my role? My explanation should make you help to understand quicker. That's why I'm going slow. Hope my pace is okay. I'm not going slow or fast. Am I being fast or am I being too slow? Or am I at the right pace?
It's
Sir,
okay,
it
sir.
is the right pace.
Right, sir.
Right.
It's okay, sir.
Thank you. Yeah. Last time, of course, when the students of 100 students, some people feel slow, some people fast, some people okay. So as long as majority of the students are okay and fine, okay. So this is where we can eliminate the segregation. Now, is there any property that can quickly tell us the flowability of the how easily the particles can flow and what is the flowability of the particles, right? Uh, is there any quick way to understand one property that gives information about the flowability of the particle is called angle of repose. One property that we can easily test is the flowability of the particles is angle of repose, right? So what is angle of repose? You just take a stationary plate or on a surface, you take a funnel and just pour the solids. You take a funnel and pour the solids. And we all know that unless the particles are very, very smooth spherical balls, always we see that the particles will form a heap. Always we see that the particle bulk matters will form a heap because of this internal friction between the solid particles and interaction between the particles. There's always formed the heap unless you take extremely smooth spherical balls. It may not, of course, if it's large quantity now, definitely that will also form heat, but very less chances. So the angle between the bottom surface to the cone side, that is called the angle of angle of repose. Angle of repose. This angle is called angle of repose. This is one way of measuring. This is one way of measuring the angle of repose. Another way of measuring the angle of repose, you store you store the you store the powder or the solids in a rectangular container. Then you just make a hole. Initially you can close with the tape, then you can open the tape. As soon as you open the tape, what we'll see, the particles will flow out. The particles will flow out, and at some point of time there will be formation of a cone. So this angle is also angle of repose. This angle is also angle of repose. Sometimes both can come same and sometimes it can vary. So there's one more called dynamic angle of repose.
Sir, can you again explain the first method?
The first method?
So can you again
Which one?
explain?
Which one? B or A?
A.
A, okay. Right. So instead of explaining, maybe I'll just show a video, right? I'll just show a video and I think it will be quick to understand. So here you can see there is a funnel There is a funnel, and through the funnel, they're pouring the solids. They're pouring the solids. When they pour the solids, what will happen? There is a cone formation. So the angle between the horizontal surface and this cone, that is the angle of repose. You can see here, so they're just taking solids, pouring it, and here it is forming the heap. It's forming the heap. So once they form the heap, the angle between horizontal surface to this cone, where my mouse is moving, that is the angle of repose. Of course, this company has shown some techniques to make consistent angle of repose formation. Like here, he just brought a scale, you know. If you put that one at the top surface, and it will give the angle of repose as 43.06. Of course, we can do simple calculation. I have anyway video kept it here, so you all can watch it later. Do you understood the student who asked the question?
Yes, sir.
Thank you. So the another video which explains the A and B, A and B. So you can see here this rectangle block and made a hole at the middle, and you can see the heap is forming, and there's a slant edge. There's a slant edge because it's a rectangle block, not a cone formation, and you can see that the particles. You can see that the particles are flowing out and forming a perfect angle, and this angle, if this angle is the angle of repose, if you're using this method, if you're using the B method. So here I think the buoyancy of stand demonstration, you can see the balls will come out from easily. There are a lot of videos on this particle technology segregation. You can watch it at your convenient time. See, this is the angle of repose. This is the angle of repose. From the heap at the bottom, if you take the horizontal and the slant edge, the angle is the angle of repose. You can also measure from this also. That is also angle of repose. Hope you all got an idea.
Yes, sir.
Right.
Yes.
Yeah, thank you. So, depends upon this angle of repose.
Hello. Sir, I have a
Yes,
doubt.
yes, please.
Sir, is the angle of repose property of the particles or it depends on the geometry of the container?
It is totally depend upon the properties of the particles only, not at all depend upon the geometry of the container.
Okay, so by any method we measure it, it will be constant for that material.
No,
Right?
no. A, B, C, if you use A, B, C, you will get different values. If it is completely dry solid, right? If it is completely dry solid and no humidity and there is no much interaction between particles, A and B always give same value. A and B can give the same value. For example, dry sand in the video I showed you. But if you take the pharmaceutical powder, A and B will not give same value. Obviously, C will never be same. C method used, dynamic angle of repose will never be same. But then what is the mean by different methods, right? You may ask question. So this table, which is talks about angle of repose versus expected flow, this is based on the method A. This table is only based on the method A. Like this, different tables, the range of angle of repose values which classifies the flow varies from method to method. Did I answer your question?
Yes, sir.
Do you understood what I'm trying to explain?
Yes, sir. Yes, sir.
Yeah. So all the values are vary. The classification table, the understanding, interpretation is constant. That won't vary. That's why there is no problem. It's just that which method you are following and which table you are referring. That is only matters. Right? So here I am showing the table here, which is gives the flowability of the particles based on the method A. Okay, in this only this method. So only this method, this table applicable. Okay, don't quote these two. Of course, this is most common way to measure the angle of repose. If the angle of repose is between 25 to 30, the flow is excellent. Meaning the particles will the flow without any hindrance. 31 to 35 also good, but the angle of repose is higher, and the flow becomes more and more lesser free flow. Lesser the free flow. If the angle is very high, like greater than 66, very poor. Means the way the particles come out from that the way the particles come out from that silo will be very poor. Free flowing is very poor. It will not come out so easily. So we need to make very proper conditions. We need to take very special care if we need to store such solids in the silos. Now, is a big important thing I have highlighted at the bottom. Although angle of repose tells the flowability or flowability of the materials, it does not correlate with the Hooper angle. It does not correlate with the Hooper angle. Angle of repose cannot be Hooper angle, right? See here, this is the angle. This angle, as I said, this angle matters the way you discharge. The way you discharge, this angle matters. But this angle will not be equal to the angle of repose. There is no correlation between angle of repose to this Hooper angle. So this is the Hooper silos, and the silos, the bottom part is Hooper, and this is the angle of Hooper. This angle has no correlation. I'm repeating, has no correlation. Angle of repose gives them an idea what type of material it is, but doesn't give any information in dealing with the design of silos. Now, what factors influences the flow of particles from the silos? Okay, angle of repose, as I said, no correlation. Then what factors? If angle of repose doesn't correlate, then what factors influences the stresses in the bulk solids? That is internal friction between the particles in the powder, cohesion between the particles in the powder that affects. Then wall friction, the interaction between the particles and the wall affects. Compressibility, nature of the particles. What is meant by compressibility? Some particles you have stored, right? And this is initially at this height. And if you for a long time, what will happen is that these particles can slowly fall down, and the height can reduce because of the compressibility nature of the particles. Then process conditions, temperature and humidity, as I mentioned. Time consolidation, like packing between the particles increases as the time increases. Compressibility and time consolidation both are interrelated. Both are interrelated. So we'll go one by one, right? We'll go one by one. What are these? What are these, and how do we estimate? And finally, we'll come to a perfect design procedure for silos so that we can achieve the mass flow. We can avoid all kinds of problems like rat hole, funnel flow, segregation. We all can eliminate that is aim. I will explain each and every part one by one. Then I'll combine everything to come to a uniform design procedure of a silo. That closes this topic of storage of solids. So first, let us take with the important property, bulk density. I'm sure you all know the density. Probably heard about bulk density, but definitely you heard about the density. Density is mass by volume. And we don't need to just give a minute and good morning, Professor Michael. No, I can take class from today also. Now actually class is going, Professor. The mechanical office going, class is going. Okay. Sure, Professor. Sure. Thank you. Sorry, students. So HOD called me, so I had to take his call. Right. So bulk density. We know the density is mass by volume of a particle. But let's say this is one particle. This is one solid. This is one solid. This is another solid. We pack all the solids in a. We pack all the solids in a container. And we know that when you pack the solids, you will not see complete filling of the solids. There will be always void spaces because of this irregular shape. Because of this irregular shape of, even if you have a uniform shape, whenever you pack the particle, there will be free spaces between the particle. That is called voids. Right? So all of us know that whenever you store the particles, there will be void spaces between the particles. So that void space, suppose, let's say we have this container, and if you store the solids without any void spaces, it made into so small powder that there is no way of the void spaces, then it will become like this. Some portion will fill with voids and some portion will with pores. So this is the total volume of the bulk solids. On the bulk storage, we have two things. One is called solids, and we have the void space or the pores. So the bulk density is nothing but the bulk solid, mass of bulk solid by the volume of the bulk solid. Mass of the bulk solid by the volume of the bulk solid. So bulk solid is nothing but the packing of a certain particles. So these are the bulk density. Now, if we take solid density, that is different. Solid density is nothing but the mass of this one solid particle by the volume of this one solid particle. So, always bulk density will be higher or particle density will be higher. Can anyone say?
The particle density.
Yes. That is simple to understand that particle density is higher because the mass of voids or the fluid filled in the voids is lower mass. Definitely, we will have the bulk density, particle density is higher than the bulk density. So void fraction, since we have the voids in between, and definitely the definition of void fraction comes into picture. The void fraction is nothing but the volume of voids by total volume. Volume of voids by the total volume. Volume, sometimes they call whatever, pores, voids, that one. So the formula for bulk density is 1 minus epsilon into density of solids plus epsilon into density of the fluid. This definition is very simple. You all can easily figure out because bulk density is nothing but mass of solid plus mass of fluid in the void spaces, but that is the total mass by total volume. So mass of solid by total volume plus mass of fluid in the void spaces by the total volume. Right? So we can do this solid volume. We can multiply with solid volume, multiply and divide with solid volume. Solid volume into mass of solid by total volume. Similarly, we can also divide fluid volume. The fluid is nothing but the fluid in the void spaces by the fluid in the void spaces into mf by V. So we can rewrite this as Vs by V into Ms by Vs. Mass of solid by volume of solid. What is this? Can anyone say? Mass of solid by volume of solid is nothing but
Rho S.
mass of solid by the volume of solid is
Density of
Rho S.
solid.
yes, density of solid, rho yes. Now volume of solid by total volume. See, this is the volume of voids by the total volume is 1 minus epsilon. If you say 1 minus epsilon, what will come? Definitely solids volume by the total volume. So that's why it will be 1 minus epsilon into rho s. And volume of fluid is in the voids is nothing but volume of voids by total volume. So there will be epsilon and so this one Vf by V. Vf by V is epsilon. Mf by Vf. Mf by Vf will be the fluid density. So that way, this formula of bulk density comes. That's the way the formula of bulk density comes. Sometimes, if the not some I just jump into this one. If the fluid in the void is gas, often right, air will be there, but often if you do inert purging with the nitrogen gases, let's say in the example which I mentioned earlier, then the void space will fill with nitrogen. If there is no purging with gases, the void space filled with air. If there is combustion inside the storage solids, then there will be CO2. Somehow different gases will be there in the void spaces. But we know that the solid density is much higher than the fluid density. The solid density is much higher than the solid. For example, air density is 1 kg per meter cube. Air density is 1 kg per meter cube. This is the typical range. Water density is 1000 kg per meter cube. Water density is 1000 kg per meter cube. Whereas solid density will be much higher than 1000. Higher than 1000. So this the ratio of the solid to fluid density will be definitely greater than 1000. So that's why often they neglect the second term. They neglect the second term. We can directly calculate. We can use the formula, or we can use this one. We can neglect the second term because density of the fluid is very low. If the voids are partially filled with liquid, let's say this is bulk solid, and the voids are partially filled with liquid. Let's say up to some position because of humidity conditions, whatever, half bed solid. If the voids are partially filled with liquid, there is term called degree of saturation. Degree of saturation. That is volume of liquid. The volume of liquid in the void spaces. Partially saturated means there is some liquid, there is some gas, right? The voids are filled with some liquid and some gas. So degree of saturation is nothing but the volume of liquids in the voids by void volume. The volume of liquid in the voids by the void volume. So if this is a partially saturated with liquid, this is the formula to find out the bulk density. Here we are neglecting this term. Here actual one will be epsilon into rho f. Will also be there, but we are neglecting because the fluid density is much lower than the so gas density is much lower than the liquids and solids. So that's we are neglecting, and this is the formula. I think all of you can derive this later. How we got this one? This is simple the way I explained here. The same thing will comes into picture. So I will just stop with these two slides. Okay. I will teach these two slides and we'll continue in the next class. Now, what are the different forces in the bulk solid? Sorry, I didn't make an animation here. It makes a whole slide messy. So please bear with me. I'm really sorry. I should have made an animation. It makes me easy. So I have taken, let's say I have filled this container with solid particles. Students, I'm sorry, it's today is mostly theory part. I had to teach these basic concepts. I know it is difficult to pay attention, but please bear with me, okay? Please bear with me. So this is the whole container where we have stored the solids. Let's say we have applied some force. We have applied some force, and we wanted to see if we take a small slice, small portion. If we take a small slice, a small portion of solid block in that big container, what will happen? What's what we wanted to see. So, yeah, sorry. Suddenly something else came in mind, so there's a discontinuity. So let's say some force is acting on this slide. I just separated this small portion where we are interested. You know, so often we take in a big one, we take a small volume element, then make the force balances like that. I've taken a small slice, small portion of the solids, and trying to see how this force acts. So this is the force acts. Whenever we have force act in a certain angle, we can make two components, right? One is vertical component, another is horizontal component, right? So the force acts in a vertical manner. We call it as a normal force, because that in case of solids that affects the compressibility or how closely it can pack. That affects the packing ability. The way the force acts in the horizontal direction, that is called the shear force. So force per unit area, the force per unit area, we know that is called stress. So the force acts in the normal direction per the area of cross section is called normal stress. Not area of cross section. I guess correct. The normal force acting per the area in the direction, the area of cross section in the direction is called normal stress. Normal stress acts in the vertical direction. Shear stress. Shear stress is acts in the horizontal direction. Similarly, just same as normal stress, shear force for the area in the direction. Suppose if you want to take in this slice, in this small one, the shear force will be so shear stress will be shear force per the on this cross section. That is basically perimeter into that height. So now, what difference? What is it? Why we have two difference? So these are the particles. These are the particles, right? When you apply some load, what will happen? When you apply some load, what will happen? The particle can move downwards, and the particle can move in the sides, both directions. The interaction in this direction is because of the shear stress. The interaction in this direction because of the normal stress. That's all. That's as simple as it is. When you apply some load on the solid particles, the particle can move this and particle can move this direction. The movement due to in the vertical direction, that is because of the normal stress. The movement due to the horizontal direction because of the shear stress, right? In the vertical direction because of the compressibility nature. In the horizontal direction because of the internal friction between the solids. Internal friction between the solids controls the horizontal movement. The compressible nature of the solid controls the vertical movement. Vertical movement. That's as simple as this, right? So, little bit more explanation on the shear stress. In fluid mechanics, you will also see the shear stress and how the stress is acting. But there is slight difference between fluid mechanics and the solids, because the behavior of bulk solids is much more complex than the fluid. Why? The distribution of pressure across the cross section is uniform in case of the fluids. The distribution of forces, the pressure force is uniform across the cross section. That's why it's called only one hydrostatic pressure. But in the solids, we have the two different directions, both plays the key role. Normal stress plays a role, shear stress plays a role. But when talking about the fluid mechanics, normal stress, we won't talk about it because the pressure forces are uniform. Please remember this point. Right? As I said, the shear stress emerges because of the frictional effects. Because the movement of solids in horizontal direction because of the internal friction between the solids or the internal friction between the solids and the wall. It depends upon the friction between bulk solid and the plane surface. frictional effects between the particles, and friction between the bulk solid and the plane surface. Obviously, rough surface will have ability to transfer higher stresses. Just let's take a simple. We have a plate and we have stored the bulk material. There is a horizontal direction. The solids will not move. Let's say we have inclined slightly. In the diagram B, we have inclined slightly. Still, there is no flow of the particles. But when you incline to a certain angle, the particles will tend to fall down. And obviously, as some particles will fall down, and some particle will show some resistance. That resistance is due to the internal friction between particles and the internal friction between the particles and the solid. That is because of that is known as the shear stress. I think stress in bulk solids, I will not rush it because as we have only 1 or 2 minutes before, we will continue from here in the next class. Okay. Sorry, if you have a next class, you may leave now and you can join next class. If you have a questions, you can ask me. I'm happy to answer. Hope my class is, and in case of teaching, there's a clarity and the right piece. If not, please let me know. If any doubts, you can ask me. We'll discuss in next class this part. I will upload the slides straight away after this class, and we'll continue from this. Student, do you have any questions?
Sir, I have doubt in containers.
Sorry, Tushar.
Sir, I wanted to ask why we need 3 different types of containers. Like why don't we just use silos or something?
Okay. Why do we need 3 different types of containers, right? Yeah, good point. So as I said, food grains are susceptible to the humidity conditions, right? If you don't maintain proper humidity conditions, the decomposition, fungus formation can happen, especially in food grains. So if you have a very large, tall containers, maintaining humidity is very hard. Maintaining humidity conditions, temperature we can maintain, but maintaining humidity conditions, maintaining ventilation conditions will be very hard. And also, you don't need large sizes for the food grains because the quantity of food grains for a certain location will be minimal. That's why they will have a bins. They will have a bins. A material where you need to maintain perfect conditions, there will place in bins because refrigeration, humidity conditions, maintenance will be easier. That is a practical constraint. Where you have to store solids in a large quantity, right? Large quantity where you need to, let's say you have a coal, you have to fill huge trucks. After mining, you have to store, then you have to fill huge trucks. So there you need more continuous processing. Whereas solids, you don't need that much. You don't need to fill trucks continuously. That's why we place food grains in bins and other minerals in the silos. Hoopers is a hooper silo or same. If it is small quantity or very in a small scale, that we call only hooper. If it is large scale, that is called silo. So, sir, did I answer your question?
Yes, sir. Thank you.
Thank you. Any students, if you have any questions, please ask me. I'm happy
Yes,
to
sir.
answer.
Sir,
Yeah.
Sir, I
One
was
question.
asking,
Yeah, Aryan, please tell me.
sir, I was asking that in the last part you were talking about bulk solids. So, like, we will not be assuming the same mechanics as that for rigid bodies, right? Like, bulk solids will follow different mechanics than rigid bodies.
Right, correct.
No, that I was confused. Like,
Yeah,
bulk
so
solids
rich
will
body
be.
you have studied in the soil, I think first year.
Yes, sir.
So we won't talk about the rigid mechanics. We'll talk about the bulk solids mechanics, which that's why I'm explaining again forces, shear stress. Shear stress part much will not come in rigid mechanics. It will come, but it
Okay,
won't
sir.
influence the flowability. It won't talk about flowability in say in the rigid mechanics.
Okay, sir.
One more student, I think, asked some question.
yes, sir. Sir, I
Yeah,
have a doubt in the C case of angle of repose.
please tell me.
Sir, I could not understand it.
Oh, you could not understand
How it
the
is
which one?
measure
Which one?
the
All
C
three or
case in angle of repose, sir.
or C case? Oh, did I forgot to explain it? Okay, so I hope still I'm sharing the slides. You're able to see.
Sir, could
Yes,
you,
so
sir, could you take this topic in the next class because we have another class to attend actually.
Oh, please. Okay. Shripad, I will explain that part in next class. Is it fine?
Okay. Okay, sir. No problem.
Yeah. Thank you. You
Thank
all may leave. We'll continue question next. Thank you. Thank you, Shanmuka Saivan. Okay, students, have a great day. Take care. Bye.
Thank you, sir.